Hello, welcome to Basics of Finite Element Analysis Part 2. This is the 7th week of this course, and in this course what we are doing is essentially an extension of what we did in the first course, which was Part 1. So, this week what we plan to do is continue the discussion of single variable two-dimensional problems. And specifically what we will learn in this week is how do we go around assembling the element level equations so that we can build a unified overall system of equations for the entire problem. So, that is one thing we will do, and the other thing we will touch upon is how do we do numerical integration in 2 dimensions. In 1 dimension we had seen that we can do numerical integration using methods like Gaussian quadrature, and we will use similar concepts or same concept, but we will extend that understanding to 2 dimensions. Once we have that, then extension to 3 dimension or 3-dimensional problems is not difficult at all. So, we will start with assembly. Assembly of finite element equations. Okay. So, let us consider 2 elements. So, let us say this is element 1, this is element 2. Okay. And so, the first element is a first order triangular element, and the second element is a 4-noded quadrilateral. In this case, it looks like a rectangle. And what I am going to do is I will specify element specific node numbers in light blue colors. So, for element 1, my node numbers are 1, 2 and 3, and for element 2 it is 1, 2, 3 and 4. And then I am also going to specify the global coordinates, not global coordinates, global node numbers. So, that is specified in green. So, 1, 2, 3, 4 and 5. Now, the first thing when we do assembly for these type of problems. So, here what we have to do is what our aim is, we will have one set of equations for the triangular element, another set of equations for the rectangular element, and we want to assemble these 2 equations together, and we want to understand how do we go around doing that. So, the first thing we do is we write down a connectivity matrix. We write down a connectivity matrix. So, let us call this connectivity matrix as matrix B, and what does that matrix mean? We will explain that. So, this connectivity matrix has certain number of rows and certain number of columns. So, number of rows equals number of elements. So, in this case we have 2 elements. So, this connectivity matrix will have 2 rows, and number of columns this corresponds to maximum number in any element. What does that mean? So, in this triangular element we have how many? 3 elements, 3 nodes, and in rectangular element we have 4 nodes. So, how many columns we will have? we will have 4 columns, okay, because that in because 4 corresponds to the maximum number of nodes in any element. So, in element 2 we have larger number of nodes, so we will have 4 columns, okay. So, now the connectivity matrix is pretty simple. So, it will have 2 rows, row 1, row 2 and okay. So, in the first row will correspond to element number 1. And what we will do is, we will write down in the global node numbers, of all the nodes of the triangular element. Okay. So, the first global node number correspond. So, we look at the first local node number, which is 1, corresponding to that first local node number, global node number is capital 1 or 1. So, that goes here. Then we look at the second local node number of element 1, it is 2, and corresponding to that the global node number is 2. So, we write down 2. Then we look at the third local node in triangular element, it is 3, and the corresponding global node is 3, the green. Okay. And because this triangle has only 3 nodes, but the matrix has how many columns? 4 columns. So, the fourth entry in row 1 is empty. So, I have just put it in X. Now, look at the second row. So, second row corresponds to element number 2. Here the first local node is number 1 and the corresponding global node is 2. So, we write down 2. The second local node is 2, corresponding global node is 4. So, the second one is 4. The third local node is 3. Oh, I am sorry, local node number is 3 and the corresponding global node number is 5, and the fourth local node number is 4 and the corresponding global node number is 3. So, this connectivity matrix is fed to the computer, because when we are developing finite element applications, we have to figure out how do we automate the assembly process also. So, this connectivity matrix is used by the computer to assemble all the finite element equations for different elements. So, what does this connectivity matrix tell us? It tells us that node 2 is common to element 1 and element 2, and it also tells us that node 3 is common to element 1 and element 2. It tells us something more. It says that the second node in element 1 is same as the first node in element 2. It also says that the third node in element 1 is same as the fourth node in element 2. Okay. So, this gives us an idea how do we enforce equality of displacement or primary variables. So, the global matrix, this connectivity matrix, it tells us that second node is common to second node of element 1 and first node of element 2 are same, which means if I am talking about primary variable u, then in that case this is the primary variable associated with the first element, which is the superscript, and second node, this equals u 1 of 2. See, this tells us element number, this is element number, and this is local node number. So, by looking at the connectivity matrix, I can write down this letter, this expression, and this equals the global degree of freedom, which is capital U times 2. Similarly, it also says that for the first element, the third degree of freedom, which is U13, is equal to, for the second element, the fourth degree of freedom, U24, right. This is C4, C3, C2 and C1, these are columns, right. So, 3 corresponds to this column, 4 corresponds to this column. Okay. So, U13 is equal to U24, and that equals the global degree of freedom associated with global node number 3, which is capital U3. Okay. So, the moment you define a connectivity matrix, from that connectivity matrix you can enforce these displacement continuity relations across the boundary of elements. Wherever two elements meet, you can enforce continuity of primary variables, because we know that primary variables have to be continuous. During assembly we have to ensure that. So, in this way we ensure continuity relation across boundaries. Okay. So, what does that mean? So, now I will write down expressions for all the global node numbers. So, what is U1? This capital letter is the global degree of freedom, which is capital U1. This equals U11, global degree of freedom U2 is common to first and second element, and that equals U21 equals U12, then U3 equals U31 equals U42, then U4 global degree of freedom is same as U second degree of freedom for the second element, and then U global degree of freedom 5 equals third degree of freedom for second element. And all these relations can be deduced from the connectivity matrix. Okay. So, using this logic we can develop a program in computer to ensure this continuity of primary variables across a boundary. So, this is one. So, this is about continuity. The second thing, when we do assembly, we learnt it in our part 1 FEA, is that we also have to do balance of forces. Balance of forces. So, what do we see? The same connectivity matrix also tells us that force at global node 2 is equal to contributions from element 1, it is due to contribution from element 1, and that is due to F21 plus contribution from element 2, and that is F22. Oh, excuse me, this is F21. So, this is about force. So, I can write similar expressions for all members of the force vector, and same thing, same logic holds for members of this Q matrix. So, I can do the force balance also. And then finally what it tells us is that, so if I write equations for element 1, I will get how many equations just for element 1? 3 equations, right? Because there are 3 degrees of freedom in this triangle, I will get 3 equations. For element 2, I will get 4 equations. Total number of equations will be 7, 4 plus 3, 7, right. So, at element level, we will have 3 equations for element 1, 4 equations for element 2. Total number of equations will be 7. When we do assembly, we will enforce this equality, and we will also enforce this equality. Not only that, we will also add up contributions, right. So, what that adding up contribution means is that I have to add up the equation associated with this degree of freedom to equation related to this degree of freedom. So, the same global matrix tells us which equations have to be added up, right, because when I have to add up forces are on the right side of the equality sign, and if I have to add up forces, this connectivity matrix tells us that you add up the equation associated with second degree of freedom for element 1 to first degree of freedom associated with element 2. Similarly, it says that add up equations associated with third degree of freedom of element 1 with fourth degree of freedom associated with equation 2. Okay. So the using connectivity matrix, we learn how to do continuity enforcement, how to add up forces, I mean this force balance, and this thing is done by adding up appropriate equations. By adding up appropriate equations. So, once we add up these appropriate equations, terms in the K matrix at element terms from, I will say, get added up, terms from K matrix get added up, and once that happens, we get a global K matrix and a global force vector. Okay. So, this is what we will do now. So, we will write down the equations for so these are the equations for the, for which element? For first element. and then we have a larger number of equations for second element, and because these are associated with the second element, I will put a superscript 2 on each of these. Okay. So, the first thing we do when we are doing assembly is we replace these local degrees of freedom with global degrees of freedom. So, this becomes U1, U2, U3. This becomes U2. What does this become? U2 to U4, U23. This becomes U5, and this becomes U3. Okay. This is the first thing we do. Then we assemble these equations, and again the connectivity matrix helps us assemble them. It is a guide to assemble these. So, what the connectivity matrix tells us is that you assemble this equation, the second equation for element 1, second equation for element 1 which is rounded in purple in connectivity matrix, with the first equation in element 2. So, we add up these two equations. Okay. And we also add up the third equation in element 1 with fourth equation in element 2. So, we add up third equation in element 1 with what is it? Fourth equation. We add these two up also together. So, the connectivity matrix is a very important tool, and once we have the connectivity matrix right, I can use this method to do assembly for one dimensional equations, two dimensional, and also three dimensional equations. The same approach holds because it is a matrix which tells how things are related to each other. So, this completes our lecture for today. We will continue this discussion tomorrow. So, thank you very much and have a great day.